In this video, you'll be exploring linear relations. Linear relations are a special type of relation between variables. A variable is a letter that is used to represent any number, for example, x. X can represent any number, such as 2, 6, -4, but a linear relation doesn't just consider the values of one variable, but rather two variables, and how the value of one variable changes the value of the other variable. For example, multiplying by 2 is a relationship. In this case, the y values are double the x values. Many different contexts in real life can be modeled using a linear relation. For example, consider this scenario in which a school is considering ordering t-shirts. The cost of the t-shirts will be related to the number of t-shirts they wish to purchase or can afford to purchase. We see some numbers in this problem. Understanding how these numbers are used to discover the relationship is essential to solving problems this unit. To explore a linear relation, let's look at a pattern. Because this pattern is made up of shapes, it is called a visual pattern. You can find visual patterns like this on the visualpatterns.org website. Let's observe how this pattern grows. In a visual pattern, we look back at each instance of the growing pattern. Each instance is called a figure, and they are numbered in order. If we extend the pattern, we can think about what later figures will look like and how many squares they have. For example, what would figure 5 look like? Next, thinking about how this pattern grows, how could you figure out how many squares are in figure 10? One way we can figure out how many squares are in later figures, like figure 10, is to look at the pattern of numbers in each figure. A table of values can be a helpful way to organize this information. Take a moment and observe the numbers in this table. What patterns do you see? You may have noticed that we can see patterns vertically, that is, in each column. In the figure number column, the numbers go up by 1 each time. In the number of squares column, the numbers go up by 3 each time. Noticing this pattern can help us determine how many squares are in later figures. Let's return to our previous question. How can the pattern in the table help you to determine how many squares are in figure 10? To answer this question, let's extend our table. First, fill in the figure number down to 10. Next, we can add 3 to move down our second column. Adding 3 to 14 gives 17, so figure 5 has 17 squares. Continuing down the column, we see that figure 10 must have 32 squares. While using the table of values worked fairly well for finding out how many squares are in figure 10, it would take a lot of work to figure out a later figure, like figure 50. So how else could we figure out how many squares are in figure 50? Pause the video and think about that. Using the patterns we saw vertically is not an efficient way of determining numbers much later in the pattern. What we'll need to do is to determine a pattern that works horizontally. In other words, we are looking for a relationship between the figure number and the number of squares. To discover the relationship, it helps to make a connection between the table of values and the visual pattern. The adding 3 each time in the table corresponds to adding 3 squares each time to build the next figure. Notice that in each figure, there are groups of 3 squares. In fact, we can see the same group in figure 1 as well. So let's add this group of 3 to all of our figures. Let's expand our table to count how many of these groups of 3 are in each group. Notice that they are the same number as the figure number. This then helps us to count how many of the total number of squares are made up from these groups of 3. How then can we determine how many squares are in each figure altogether? What is the difference between the numbers in these columns? Let's add another column to our table to count the missing squares. You may have noticed that the only squares left to count are the green ones. And in each figure, there are exactly 2 green squares. So to determine how many squares are in each figure, we multiply the figure number by 3, then add 2. We have found the relationship, and we can use the same relationship to determine how many squares are in figure 50. There are 50 groups of 3 for a total of 150. Adding 2 for the green squares gives us a total of 152 squares. Notice that there is another way to see this visual pattern. Rather than groups of 3, we can see 3 groups, and the number in each group is the same as the figure number. Your child should be encouraged to try to see visual patterns in more than one way. Let's generalize this pattern for any figure number. We can use a variable, such as n, to represent the figure number. Looking at our pattern, how could you determine how many squares are in figure n? First, we multiply n by 3, which is written as 3n. Then we add 2. Our general expression for this pattern is 3n plus 2. Because it contains a variable, it is called an algebraic expression. Let's take a closer look at this general expression and the terms that make it up. The 3 corresponded to how the numbers grow in the table, as well as how many squares were in each of the n groups. This number 3, which is multiplied by the variable, is called the numerical coefficient. We notice the 2 at what was added in each row, as well as represented by the green squares. The 2 is called the constant, because no matter what the value of n is, the 2 is always the same. So far, we have seen this pattern represented visually with the squares, numerically in a table of values, and algebraically with the expression 3n plus 2. Next, we will explore how to graph this expression. We begin by drawing 2 rays, which are called axes. Next, we label the axes. The left column is represented by the horizontal axis, and the right column is represented by the vertical axis. The axes are actually number lines, so here they both begin with 0, and then proceed in a positive direction. The numbers indicate that we are using one space in the grid to represent a value of 1 on each axis. To plot a point from the table, we first begin with a starting point. Because it's a starting point, it is called the origin. The first figure number is 1, so we move one space along the horizontal axis. The corresponding number of squares is 5, so we move 5 spaces up vertically. This point represents the first row of the table, and we label the point using these numbers. This label is called the coordinates of the point. In a similar way, we can plot the remaining points in the table. Notice that the points lie in a straight line. That is why it is called a linear relation. Although these points lie in a line, not every point on this line is part of the relation. For example, this point here does not fit with the pattern, because it would mean that figure 1.5 has 6.5 squares, which is nonsense. Generally, if a context, like this visual pattern, has no meaning for points in between, it is called a discrete relationship. In a discrete relationship, we plot points, but we do not draw a line through them. Just as we made connections between the algebraic expression and the table of values, we can also make connections to the graph. Let's zoom in to one section of the graph. Notice that to go from one point to the next, you go up 3 and right 1. This fraction is equivalent to the number 3, which corresponds to the numerical coefficient in the expression. Because this fraction describes how the vertical change compares to the horizontal change, it is called the rate of change. We see this consistent rate of change as we move from one point to the next. Note that the rate of change applies between any 2 points. For example, 6 divided by 2 also equals 3, and we can see this rate between these points. Or -6 over -2. But what about the +2? Where do we see this in our graph? Let's insert a row into our table and consider figure 0. Recall the rate of change. Now let's apply it in reverse. This takes us down 3 and back 1. We see that the number of squares for figure 0 is 2, which corresponds to the 2 in the algebraic expression. Even with our visual pattern, we can imagine why figure 0 has just 2 squares. Usually, linear relations are described algebraically using 2 variables. For example, y equals 3x plus 2. The column headings now become x and y. And in our graph, the axes can be labeled x and y. Now that we are no longer in the context of a visual pattern, we can extend this relation to include negative numbers, both to the left and down. As we did before, we can extend our relation to the left by going down 3 and back 1. This gives us the point -1, -1. Continuing the relation gives us the point -2, -4. Because there is no context, it makes sense to draw a continuous line through these points. All of the points in the line satisfy the equation of the linear relation. Let's summarize what we have learned. In a linear relation expressed algebraically, the number that is multiplied by the variable is called the numerical coefficient, and it also refers to the rate of change of the relation. The term that is added or subtracted is called the constant. Putting these ideas together, we can summarize the equation of a linear relation as y equals the rate of change times x plus a constant. You will see later that the rate of change in the constant can be negative integers, and in grade 9 they can also be fractions or decimals. A linear relation can be represented in many ways: algebraically, a table of values, or a graph. These representations are all connected. The rate of change shows a constant rate in the table and shows a constant change between points in a graph. The constant is the y value in the table when x equals 0. This is because when 0 is substituted for x in the equation, it equals 2. Finally, the constant is the value on the y-axis where the line crosses it. Now let's apply all that we have learned to some sample questions from the textbook. First, let us return to the context presented at the start of this video. A school pays $125 to design a t-shirt. It costs an additional $15 to make each t-shirt. There are many different questions we could answer about this context, but a good starting point is to model the situation using a linear relation. To model a situation means to write an equation that fits the context. Think about the situation and what you've learned, and try to think of an equation that fits it. To develop our equation, first let's define our variables. Let C equal the total cost of the t-shirts, and let's let N equal the number of t-shirts ordered. We know that they have to pay $125 up front, then $15 per shirt. One approach to developing an equation is to use a table of values. For 10 t-shirts, it would cost $150 for the t-shirts plus the initial $125 for a total of $275. We can try other values as well. From the patterns in the table, we see that we need to multiply the variable n by 15, then add 125. Our equation is C equals 15n plus 125. A more direct way to determine an equation of the linear relation is to think about the meaning of the numbers in the problem. The $125 is the constant because that value remains the same no matter how many t-shirts are ordered. The $15 is per t-shirt, so that corresponds to the rate of change. Using our general equation, we can substitute in the values and determine that the equation is C equals 15n plus 125. Once we have the equation, we can solve several kinds of problems. For example, think about these problems. Think about how you could use the equation to solve them. To solve the first problem, we need to use substitution, which means to replace a variable with a number. In this case, 378 is the number of t-shirts, so we need to substitute for n. This works out to 5,795, so it would cost $5,795 to make 378 t-shirts. For the next problem, this time we are given the total cost, so we need to substitute for C. We now have an equation that we need to solve for the variable n. To do so, we need to isolate n, which means to get it on its own. A first step we can do is to subtract the 125 away from the right side. But in order to keep the equation balanced, we need to subtract 125 from the other side as well. Next, we need to divide the right side by 15, and so we also need to divide the left side. This solves n to be 148, so if the school spent $2,345, they ordered 148 t-shirts. In this next problem, we are asked to create a graph and a linear equation to represent this table of values. First, let's create the graph. On this grid provided, we first need to decide where to put the axes. Look at the numbers in the table and think about where a good place is for the axes. The h values go from -3 to 3, so it makes sense for the vertical axis to go down the middle. We label this axis n to represent the values in the second column of the table. The highest n value is 0 and the lowest is -18, so we need our horizontal axis near the top of the grid. We also do not have enough spaces on the grid, so we will need to make every space have a value of 2. Mathematicians call this a scale of 2. Now that we have our axes set up, we can plot our points. -3, 0 is plotted where h equals -3 and n equals 0. The rest of the points are plotted in the same way. Next, let's develop the linear equation for this graph and table. We need to identify the rate of change and the constant. From the table, we can see that the rate of change is going down by 3, related to going up by 1. So our rate of change is -3, which we also can see in our graph. In our table, we know that we can get the value of the constant when h equals 0. So the constant is -9, which we also see as the point on the graph that intersects the vertical axis. So our equation is n equals -3h minus 9. We can verify our equation by trying a row from our table. Substituting 2 for h and -15 for n shows us that the equation is true. So our answer has been verified. Our final textbook problem is an application involving water pressure. Scuba divers experience an increase in pressure as they descend. The equation P equals 10d plus 102 models the relationship between pressure and depth, where P is the pressure in kilopascals and d is the depth below the water surface in meters. Graph the relationship for the first 50 meters of diving depth. Let's begin by drawing our axes and labeling them. The amount of water pressure depends on the depth, so the horizontal axis is labeled depth and the vertical axis is labeled pressure. Next, we add the units for each. We need to graph this equation. A table of values would be a helpful strategy to do so. Begin with a diving depth of 0 because it does not make sense to consider negative values for depth. Next, fill in the table with other values up to 50, and going up by 10 makes sense. When we substitute 0 for d, we get 102 for p. Similarly, we can fill in the rest of the table by calculating. First, let's label our graph, our axes, and the origin. Next, look at the values in the table to determine an appropriate scale for our axes. Let's use a scale of 10 for each space horizontally, and a scale of 100 for each space vertically. We can now plot our points. With such a large scale, we just need to get the points in approximately the correct places. It makes sense to draw a line through these points because depth is measured continuously. Now that we have a graph, we can use the graph to solve other problems. For example, what is the approximate pressure at a depth of 15 meters? Let's zoom in to this part of the graph. First, mark where a depth of 15 meters is. Next, draw a line vertically until it hits the graph of the linear relation. From this point, draw a line horizontally to hit the vertical axis. On the vertical axis, this is approximately a value of 250. Let's check our solution using the equation. Substituting 15 for d gives us 252, so 250 is a reasonable estimate. A common mistake that students make is when writing an equation to represent a table of values. We can see that the constant for this table is 2, but for determining the rate of change, the common mistake is only to look at the y values. In this case, +6. So one might think that the equation is y equals 6x plus 2. But the rate is how the y values change in relation to the x values. So our rate of change is actually positive 6 over positive 2, which equals 3. So the correct equation is y equals 3x plus 2. This video addresses several learning standards in the Mathematics 8 curriculum. First of all, this big idea is addressed throughout the video. Most of the linear relationships we explored were discrete. We represented them using equations, tables, and graphs, and we made connections between these representations. These representations helped us to generalize the visual pattern we did at the beginning of this video. In content, we looked at discrete linear relations, which is also a standard in grade 7 and grade 9. In grade 8, this standard extends to larger numbers but still remains limited to integers. Your child will explore linear relations using decimals and fractions in grade 9. We also looked at expressions when we wrote equations and substituted in values to evaluate them. Finally, we solved two-step equations to solve problems. There are more types of equations your child will solve this year than the ones in this video. Several curricular competencies may emerge as your child learns and applies the content from this unit. We used reasoning when we generalized the visual pattern. We modeled when we wrote an equation to fit a particular context, for example with the visual pattern and with the t-shirt problem. We used multiple representations of linear relations, a table of values, an equation, and a graph. We also showed the connections between these representations.